Hello everyone, this is Mustafa Sadiq Al-Jumaili, and today we are going to talk about one of the most important updates about large language models, which is the RAG, or the Retrieval Augmented Generation. This is actually one of the, as we said, most important additions to the large language models that was released during the end of 2022 with the ChatGPT 3.5. And since then, we saw a lot of advancements and developments in the large language models and the generative AI, uh, mostly because of this retrieval augmented generation, or the RAG for short. This is part of the course MDS 504, which is the Advanced Machine Learning course. This is within the module 4, which is the Transformers for Sequence and Multimodal Artificial Intelligence. Okay, so first of all, we will talk about why we needed the RAG, or the Retrieval Augmented Generation, in the first place. As many of you may remember, that when the ChatGPT 3.5 was released by November 2022, we had a lot of problems, specifically the hallucination, where there was this cut-off point where these models were trained on specific data for specific amount of time. So it had no idea about what happened after this period of time. So whenever we gave these models, or large language models, any query from the users, we hit like what is called the static training data wall, where there is this knowledge cutoff that these models don't know anything about the world that happened after they were trained, because they froze in time based on their latest training data or date. Then, because these models were trained to always give an answer, they didn't say we don't know. So they usually give us a lot of answers that looks plausibly sound, which is like they sound correct, but they are incorrect. So we called it hallucination, which was a big problem for the initial generations of these large language models. Then there was this lack of provenance, which means that when we asked these models about the reference for these information that they are giving us, specifically when we know for sure that this information is wrong, they couldn't dig deep and give us the reference or the resource for this information. All of these problems caused the people who are trying to develop these large language models to work on something called retrieval augmented generation, which means that instead of only depending on the data that we already trained these models on, we go a little step further by allowing these models to have access to the trained model, to the trained database, and also to an external database, which can be the internet or a private database that can be for a company, organization, government, anything else. So in this time, instead of telling these models to just go and bring the answer from the stored database, no, you can go and search the internet or the open database that you can access, then combine it with the question from the users, then produce the plausible, provable answer that can be linked to a reference or a resource that is up to date, and it is more surely correct than the original things. In this table, you can see that there is like this comparison between the standalone large language models, like the model that we saw in ChatGPT 3.5 and the previous models. Then there is what is called fine-tuned large language models, which is when we just take these open source large language models and we fine-tune them by training them on our specific data for our company, our government, our university, or organization in general. And then these large language models that are based on the RAG augmented, or retrieval augmented generation. And we can see that clearly that for the knowledge currency, the best is RAG based ones. For the risk of hallucination, which will be the lowest for the RAG augmented. For the citation and the provenance, it's also exact and verifiable resources or references that we can get even the link for these references from the RAG augmented large language models, which we already started seeing in the ChatGPT 4 and the models after that. For the computational cost, it is also low because we use these open source models or the available models, and we just allow them to access the external database or data vectors that we will talk about shortly. So we can see that retrieval augmented generation is most efficient architectural paradigm that makes large language models smarter without massive computational overhead of the full model fine-tuning. So here in the retrieval augmented generation, we are balancing between the generation from the large language model or the generative AI and the retrieval. So the RAG gives us information retrieval and natural language generation or natural language processing. So the retrieval will be querying a specific authoritative knowledge base outside of the model's initial training data. And then the natural language processing or the natural language generation will use the large language model strictly as a reasoning and articulation engine to synthesize the retrieved data. So we are combining the goods of both sides. This also shows a comparison between the hallucination engine versus the grounded engine. In the hallucination engine, as it is called, we used to have this query from the users when they are chatting with these large language models. Then there is this opaque large language model core that will give us unverifiable data or output, which is usually, as we said, has a big chance of having hallucination and wrong answers. Whereas in the grounded engine that is using the RAG augmented generation, the query will go in both sides. It will go to the external vector database to retrieve the most up-to-date and recent data that is verifiable and authentic, and then it will go and search its engine or its data model, AI model for synthesis engine, large language model, and then it will give us the verifiable cited output that is more accurate than the original case. Here to know a little bit more about the architecture of these RAG retrieval augmented generation large language models, there is this 5 stages pipeline that started with the ingestion of loading the raw data or documents in different data formats, then chunking or cutting the data into or breaking the text into uniform semantic segments, then the embedding, which is converting this text or natural language into numerical vectors or mathematical translation via spatial modeling. Then we will have this vector database, which is high dimensional storage and indexing for this data. And finally, the retrieval and generation, where whenever the user is giving the a query to the large language model, it will do exactly as we saw here. It will just go for this external vector database, and then it will go to the large language model trained model to search for the similarity and strict context injection, as we will see in these steps in this like detailed explanation. So for the stages 1 and 2, transforming raw documents into uniform segments, as we mentioned, first we are loading the documents and ingesting the documents by converting varied data formats like the PDFs, the raw texts, or SQL servers or databases into a single standardized plain text format for the processing pipeline. So whatever the source of data or the type of data or the shape of data, we are just unifying them as a plain text format. Then we are chunking them, breaking long documents into smaller, systematically or semantically meaningful segments. This ensures the subsequent mathematical models will process focused, contextually dense packets rather than overwhelming walls of text. So by chunking or tokenizing the documents, we make sure that each chunk is, or the target size is almost 500 tokens, more or less, depending on the window or the type of the document, to make sure that the mathematical modeling and mathematical calculations will not be very complex or very long. Then the embedding step, where we are converting the text into semantic vector space, which is like high dimensional vectors of numbers that are representing the different meanings or semantics or words in the natural language, where we can use different models like the OpenAI text embeddings 3 or the Hugging Face to convert the discrete text chunks into a high-dimensional numerical vectors. This means that using the language, the meanings are mathematically mapped into a spatial coordinates into this higher dimensional space where there are many dimensions, and we can see here from this visual that, for example, the medical concepts will be closer to each other and the legal concepts will be closer to each other, but they will be far away from each other because each of them will have different embeddings, different vector space. So whenever we give a question, we will see that depending on the text or the terms that we use in the question, it will go for the medical concepts or the legal concepts or whatever concepts that are there in this multi-dimensional space, which is higher dimensional space. Then how can we say that our question is closer to the medical or the financial or the legal or something like that? It is based on the similarity matrices that are navigated through the vector database. And usually we can see this similarity through search by cosine similarity or Euclidean distance. Cosine similarity by using angles, and the Euclidean distance by using the straight lines to calculate the closest terms or the vector space to the terms in the question that we gave through the query to this large language model. Finally, this is the grounded prompt interface, which is forced context adherence. Unlike the previous large language models, which you only depended on the saved text in it or saved knowledge, here we give the system instructions to answer the questions based only on the provided context. Then we retrieve the context or the top K chunks from the external database. Then we use the user question to find the closest chunks to this question, where the large language model will never rely on its internal memory. It functions purely as a synthesis engine, reading the retrieved chunks and generating an answer strictly bounded by the injected context from the user, of course. By doing so, we are making sure that we solve the three problems that we talked about in the beginning of this lecture, that are hallucination by forcing the system prompts, clamping the context window, eliminating the model's need to guess. So there's no guessing. It is just using the information that it is already trained on and retrieved from the external sources. So it will be grounded and more authentic and more verifiable. The knowledge cutoff will also be solved by using the external vector databases that can be up to date and updated in the real time without retrieving or retraining the entire model, which will give us dynamic retrieval. And finally, the lack of provenance. That is the original one of the three original problems that we had. Now, because the exact chunks are retrieved mathematically, every claim maps back to its source document. So here we can give the links or the sources or references or resources to every claim that we give in our answer, which is based on the similarity mapping. Finally, as we said, with the large language models that has a huge amount of hallucination in the beginning, it was a lot of sectors were reluctant to use them specifically into sensitive fields like the legal or the financial or the military or the medical fields. But now, with the retrieval augmented generation, it is like chatting with thousands of papers, state-of-the-art papers, and finding highly specific methodologies, comparisons instantly, unlike the previous large language models. Now we have a corporate knowledge database because you can get answers from to complex HR, engineering, technical questions by referencing exclusively internal private organizational manuals without bothering any one of your colleagues in the team. And also for the legal and medical fields that were very sensitive and were not very motivated by using the hallucination large language models. Now you can generate diagnostics or case summaries where every single claim generated by the AI is accompanied by a direct, verifiable citations, references, resources, or even links, direct links. So this will makes the large language models more plausible, more welcomed into different sensitive fields around the world. Finally, the three pillars of the deployable enterprises means that you can now deploy large language models within your company by ensuring accuracy, which is delivered through the mathematical vector retrieval, the currency, which is delivered through the dynamic external document ingestion, and the transparency, which is delivered through the explicit provenance and the citation. So retrieval augmented generation is not merely an incremental tool, it is a definitive architectural paradigm required to deploy large language models in a professional and industrial settings. That's all for today's lecture. I hope that it was good and useful for everyone. And I hope if there is any question, I will be happy to answer all of these questions. Thank you so much.